All right, hello, and welcome to our second class. I have to apologize to this class in particular. I am so very sorry that my message did not reach you on Tuesday. I thought I had sent an email to both sections letting you know that I was sick and not going to be able to make it to the lecture, so I can only imagine how frustrating, confusing, and annoying that must have been to just be sitting there in the classroom waiting for your professor to show up only to see that he just never did. So I'm terribly, terribly sorry about that, and I will absolutely make sure that doesn't happen again. So for those of you who do find this, thanks for joining. I appreciate it. And if you'd like to, please feel free to say something in chat. I think there's about a 10-second delay, something like that. So let me know you're there. That would be great. In terms of the course as a whole, I expect we're going to have to shift the exam schedule a little bit, or move the content a bit. So I haven't planned any of that yet, but I'll try to make up some ground. I expect, though, that we have to move things a bit, given now two classes canceled. So bear with me and expect a bit of a change in that. In the next, probably next week, I'll sort things out. Okay, so with that, and while I still have a voice, I'm gonna pick back up where we left off last time. If you recall, we had been talking about mass balances as some change in the amount of stuff in a system as a function of time. So mass per time accumulation rate, or as defined as the combination of the input rates across some control boundary. We call the edges of the circle a control volume or a control boundary. And what we're looking at is any inputs going in across that boundary compared to anything exiting. We have any which direction, any exiting, plus any reaction plus or minus happening there. Okay, so that's the context. That's our essential mass balance, is the writing that out in that manner. Accumulation is equal to what's going in, what's going out, plus whatever reacts. So we took a very simple case here with this problem to look at, okay, well, what is that? How does that work in practice? Just to kind of get our minds thinking about solving problems with that particular approach. Now, what you'll find is you could solve this problem without this approach because it's simple enough that your intuition could solve it for you. Where it will get more complicated is when we do add reactions into it, the way we have to care about those, and sometimes when we add in the different outputs or different pieces of the puzzle here will complicate things a bit to the point where it goes beyond what our intuition can do for us. So this one, I had suggested that you try it in class and take a look, and this is the point where we arrived at. We said that, well, accumulation will be 0 because it's just the chloride is dissolved in the water, two water bodies flowing together, two rivers or streams, forming one, other one leaving. There's nothing that would cause the chloride to get stuck and accumulate here. There's no reaction happening. And so the net accumulation is 0. But if we want to find out, let's say, the concentration in the mixture, we can use the mass balance to figure that out. Because we can write this as the inputs, the CS coming in, plus the CW coming in, ultimately mixing and forming the CM. So that's the process here. So we've got this equation. We can go ahead and fill in the numbers here, we could say 20 milligrams per liter for the CS and 10 cubic meters per second for the QS, plus 5 cubic meters per second and 40 milligrams per liter for CW. So the question is, what is CM? But we also actually don't know QM yet. And if you think about it, one thing that can happen is we could do this whole entire mass balance just on the flow of water. It would be even more simple, right? We have 10 coming in plus 5 coming in and some unknown amount going out. No reason we have any accumulation of water. There's not a dam here or anything like that. So we would assume that the water accumulation is 0. Now you already can see that this should be 15, right? That QM should be 10, so the QS plus QW. And so what I'm showing again is just that really our intuition can get us there for a lot of it, but we could also take this elaborate mass balance approach. So that would be 15 cubic meters per second, and now we have enough information to solve this. So we've got, coming back to solve for our CM here, on the left this is 10 times 20 is 200. Turns out 5 times 40 is also 200, so we have 400 here. The units are a little funny, but they're about to cancel out because we're about to divide by Q, right? So this would be milligrams per liter times cubic meters per second are currently the units. And I'm just gonna, we could convert liters to cubic meters and cancel and convert and all that, but we're about to divide by 15 cubic meters per second, so that will all cancel nicely, times CM, which we want to solve for. So it turns out, did this just a bit ago, CM should be 26.7 milligrams per liter. And if you stop a moment and think about it, another thing we can do just intuitively is see that, well, this number, the answer of these two streams combined, should be somewhere between those values. So it should be between 20 and 40, and sure enough it is. And then we could also stop and think about another obvious thing would be, well, if these had the same flow rates, if it was 10 and 10, then we just expect it to average to 30 milligrams per liter. But that's not exactly true. In fact, 1 is lesser, so we expect this to have a smaller contribution, so it should be less than 30. We can kind of just see it that way. So thinking in that type of manner might be a good way to check your work sometimes. All right, so at any point, please do feel free to comment. I'll see it, and you'll probably see it pop up on the feed as well. I have it set to display for anybody who's not even has the comment box up. So please feel free to comment, say hi. You're even welcome to talk with one another if you like, ask questions, any of that. Okay, so we have some idea of a mass balance. Well, what do we do with it? The plan next is to apply it to practical situations that we can design some operations accordingly. So here we have a picture of this is a wastewater treatment facility that has aeration ongoing, and this aeration is essentially providing air for bacteria to consume the waste and convert dissolved stuff into bacterial particles that then you can separate out easier. But I'm showing you this because the bubbling here is clearly going to cause it to be well mixed. It's going to be constantly mixing it. That'd be a lot different if we had a slow-moving water that was not turbulent at all. It was laminar flow and all that. Especially if we channeled it into a kind of a narrow passage, the mixing would be so much different if it was flowing through a small channel that was not bubbling compared to this big wide channel that's bubbling the whole way. So in this case, this particular reactor looks like it's continuously mixed, and it very likely has some flow going in and out. So that we'll see in a few minutes, we would call that a continuously stirred tank reactor, or there's a couple names for it, but that would be one. So we're going to come back to these different reactor types in a moment, but first we're going to take a look at the reactions themselves. So we need to be able to know if we have our mass balance and we have some accumulation term, we have input rates, output rates, plus some reaction term or reaction rate. We want to know how to mathematically put this term into place. So the next several slides, we're going to dive into what does this reaction term look like and how does that depend on the nature of the reaction itself. Okay, so when I say the nature of the reaction itself, what I'm referring to in particular is the reaction order. Now, when I jump in and describe different reaction orders, it would be pretty easy to go in and talk about it, pretend like you should know it, and it should be common knowledge and all this. And the reality is, I could lose you, but even though you actually have seen different reaction orders in real life all over the place. So I'm going to take a moment to explain. When we talk about a reaction order, this doesn't have to be chemical reaction, it could be a physical reaction, could be biological reaction, and as you'll see with some examples, it could just be a system, a money system that is working, right? So when I'm talking about a reaction order, the order, which is typically zero order, is first order or second order. What I'm referring to is to what extent does the change that's happening depend on the amount of stuff you have there. Okay. To what extent does the change that's happening depend on the amount of stuff? For example, if you have a bank account and you're earning some interest in that savings account, the amount you earn will depend on how much you have there. If you have a fantastic interest rate of 10% and you have $100 in the account, then you'll get $10 over some period of time. Let's say that's a year. So 1 year later, you have $10 more. If you had a really bad interest rate, 0.1%, but you had $1 million in that account, you're going to be earning a lot more money in that year, right? If I do that math, that's probably $1,000 or $10,000. So having that rate corresponded to the amount of money you have there makes that, in that case, that's a first order because it depends one time on the amount that's there. So you've actually seen first order rates in a lot of scenarios. Now, to use one other money example, for a zero order where it does not depend on how much is there, it depends to the power of zero, as we'll see in a second, that would be like adding $20 to a bank account every month. It doesn't matter how much is in there, you're adding $20. Okay, so that would be kind of like an income, just that's what it is. It does not matter how much is there. Okay, so to write that out mathematically, we would say we have some rate of change of C equals, and we can write it as dc dt, so a really tiny change in C per really tiny change in T, that as we analyze that equals either a growth equation or a decay equation, so plus or minus, K, this is some rate constant. This would be like your interest rate, for example. Times C, which is the thing that we're interested in changing or tracking the change of. So that would be like money in a bank account, to the nth power. And this is your reaction order. Okay, so you'll see for a zero order reaction, the way this would write out would be, and I'm going to give first a decay example for each of these. So dc dt equals negative k c to the 0 power. And you know that c to the 0 power, anything to the 0 power is 1. So this is just equal to negative k. And what that would look like if we graphed a plot of C changing with time for a decay reaction should be something a little bit like that, right? Some line, the slope here would be K, and it's in the negative direction. Okay, pretty simple. This would be the 0th order reaction. So a first order would then be dc dt equals negative k times c to the 1 power, which is just negative kc. And then we'd get an exponential decay. And at first, the amount of change in concentration per change in time is a little bit large, but as we have less C to change in the first place, we get less change because it's proportional, right? So you've seen, the interest rate example. It's proportional. It's some percentage earned per year or whatever, or per month, or however you want to define it. It's proportional to the percent of the balance. So it's like a percentage. So we'll look at the units of that in a couple minutes. So then a second order would simply be dc dt equals minus kc squared. And that's just kind of what you have. So in that case, it's a lot like the first order, except more extreme. It's a power law. Something like that. Okay, now bear in mind that we could do all of this with a positive k, and then it might be some positive line, or equals kc for a growth equation, and then it would look something like that. So if you had growth instead of decay, it's going to look a lot different, right? And just imagine I drew those as imagine I drew them well. Oops. Okay. So any questions about that? These are the rate orders. This is kind of what we're talking about if we ever say a zero order or a first order, second order equation. These reaction terms, this R of C, will be embedded into that reaction term. Typically, what we need to do is say that this term is actually going to be, what I'll do is I'll say this is going to be equal to the volume of some reactor times R of C. Okay, so that means we're placing this right there. that gives us a way to put our reaction term into any mass balance. All right, so what about the units for these reactions? And I'm going to pay close attention, or ask you to pay close attention to these units, because you'll get word problems that may or may not tell you the reaction order. So then you have to stop and think to yourself, well, I'm making this mass balance, but I don't know if I need C to the 0 power or C to the 1 power or what. But once you know the reaction order, you know what to do there. And if you know something about the units that you're working with, then you should be able to know your reaction order. And the reason for that is because with these terms, if you look, the dc/dt must have some units of concentration. In this case, we'll say milligrams per liter per time. In this case, we'll say seconds, in order to just exist, right? That's just the nature of dc divided by dt. It's a concentration over time. So that means that the other side of this equation must match. So that simple principle there, it just has to match, is all we need to work with. So for a zero order reaction, the rate constant is going to cause this side to match the left side. And because C to the 0 power goes to 1, pretty much unitless, then K has to have milligrams per liter per second as its units. Okay, so C to the 0 power didn't give us any meaningful units, so we're going to ignore it. So that means if you see a reaction rate constant that is listed and it says some reaction, let's say milligrams per liter per second, then you know that's a zero order reaction. You don't have to know anything else about it. You already know that's a zero order reaction. We'll talk a little bit about a complication when we get to disinfection, because we can combine it, a concentration that's held constant of the disinfectant with the rate constant itself, but we'll come to that a good bit later. So for now, just recognize that that would be a zero order reaction if you saw it that way. Now, one other note I have here is, again, if we had let's say a decay reaction like this, and we wanted to take the derivative of that, well, the derivative of a linear line is going to give us a constant, right? So this would be some negative value constant. The amount that's changing over time is not changing over time. So the dc/dt per over time is just constant. I guess maybe until we run out. Okay. Like I said, anytime, please do ask questions, and I'll see them a few seconds later and be able to respond to you. All right. First order reactions are quite similar. We have the same exact process. Over here, we have to match. We're going to use milligrams per liter per second again as an example. So K times C to the 1 power has to match these. So if C is in milligrams per liter, and we need milligrams per liter per second, then what we get from K has to be 1 over seconds in order to get a final unit of milligrams per liters per second. So in a first order reaction, we would say seconds to the -1. Now, that probably feels a little funny. It's like, well, we're talking about milligrams per liter of this stuff. Why is it that we are not quantifying this reaction rate constant in that manner? Wouldn't you kind of have to, right? Well, it turns out that we've already mentioned first order reactions. And once you see this, you'll start seeing it everywhere. A common first order reaction would be an interest rate. And in banking terms, what you'll very often see is some advertisement for, I don't know, 3.0 APR or sometimes APY. And what they're talking about is an annual percent return or yield. And so really this this unit is a percentage, so a portion. It's kind of like there's no unit there at all. It's just 0.03. And you could do year to the minus 1. And that's the same thing. So when they say 3.0% per year, as a fraction, that's 0.03 of the total every year. So as a rate constant, we could write that as a K. There you go. And then you see now, this K has units of per time. It must be a first order reaction. So when you see any sort of banking thing, any investment stuff, maybe mortgage rates or whatever, next time you can stop and think about it and say, hey, there's a first order reaction. It's got per time units. It's just hidden because, this whole APR stuff. With that, you can see now that a first order reaction is just a proportional thing. And so because it's directly proportional to the amount that's there like that, we don't actually ever incorporate the milligrams and liters in the actual rate constant. Okay, so we drew this one before. We have the exponential decay for a decay reaction, and that means if we were to take the derivative of that, that should be a constant change in the amount that's changing over time. Okay. Last would be the second order reactions. We're not going to use these very often. The math to incorporate them properly into mass balances can get tricky because you have the exponent. It's not impossible, and there are several tables that we could use and stuff. But really, for the purposes of our class, it's mostly never necessary. So I'm just going to kind of show you that it's pretty much the same process. In order to find the units, again, we have milligrams per liter per second over here from the dCdt term, and that needs to be equivalent to essentially what is milligrams per liter squared. Right? So we actually have to undo one of the milligrams per liter, and so the K has to adopt an inverse of that, liters per milligram, and we need the per second there to add in that time element. Now, this actually looks pretty close to the zero order reaction, because the zero order reaction was milligrams per liter per second from K. So don't get too confused there. Remember that how you set it up, has to essentially match your dCdt. That's the thing of it. All right. So with that, we have this system. The rate constant is liters per milligrams per second. We plotted this as our kind of power law sort of thing. If you derive that, that's going to become the exponential decay to look a little more like that. Of course, all of that depends on this, the steepness of the rate constant itself. All right, yeah. So I don't expect to be using second order reactions, or maybe in an example sometime I'll kind of show you what it would be like, but it's rather rare. You should be able to identify the units or derive the units for any of these because, again, this is a rudimentary unit analysis situation. Okay, so now we have some idea of that reaction term, right? So we now know something about how to find R of C, and I guess we called it a lowercase r. So R of C that goes into there, and we'll multiply that by whatever volume we have. That's going to give us our reaction. And if you stop and think about it, what we called R of C, that was dc dt. And if we multiply that by volume, what are we getting? We have a concentration per time times a volume yields us a mass per time. And I've told you already that each and every one of these rates needs to ultimately be a mass per time. Right? So that's the deal. Now I want to talk about the reactors in which this reaction term can go and exist. It can, we could put it in different scenarios, and depending on what are the conditions around, that will tell us something about, are we expecting accumulation? Do we have any inputs and outputs? What's going on in this particular scenario? Okay, so a batch system is essentially like my water bottle. It is, may or may not be closed, but it can be mixed, can be well mixed, and you can treat a batch of water or whatever at a time. And so you give it a certain amount of time. We would, for an ideal reactor, we're going to focus on ideal reactors. I'll show you a little video of a non-ideal reactor just to kind of give you an example and to be thinking about what the reactors might look like and the residence time and all that. But for an ideal reactor, a batch one would be completely mixed, perfectly mixed, has no inputs and outputs. It would just be there as a holding tank, a vessel for your water. So that'd be batch. Then a CSTR is what I will call it. Continuously stirred tank reactor. You'll see it occasionally called like a CMFR, continuously mixed flow reactor, or a CFR, continuous flow reactor. Some versions of that, but it's basically continuously flowing and it's well mixed. That's the point. So this is like taking a batch reactor and adding a hose, dumping some water in, and a hose taking some water out. Now, what we'll see is this makes an interesting situation that whatever we are adding in is immediately mixed all around if it's truly ideal, like we assume, and it's truly perfectly mixed. Then as soon as we put something in, a small portion of that is now flowing out. And so that actually does a couple things for us. One is it kind of makes the drop in concentration. Let's say if we have a reaction removing stuff in here constantly, then as soon as we add stuff to it, it will be diluted because we have that drawdown force of the reaction removing stuff. And so as soon as we're dumping water in, we're getting out water that has a lower concentration if we're removing this contaminant. But that also means the water doesn't have as long on average to spend inside this chamber, and so our treatment typically doesn't reach as high of a level as if the water stayed in there longer time. So sometimes the CSTR is a great fit for some purpose. Maybe we're trying to remove 90% of some contaminant, and just a CSTR or maybe two in series does a great job at doing just that. But sometimes we might want to operate a system where we really give it a longer time for the reaction to occur, and then what we would look for is a plug flow reactor. So the PFR stands for plug flow reactor. And a plug flow reactor, basically we can think of it as a small little slice of water, a plug, that is flowing through a channel in a way that it can't mix with the other plugs around. So if we have one here and one here, the water is not mixing across. That's not happening. So the water is just kind of staying in a little plug, theoretically. And at least in terms of the flow dynamics, if you have an ideal plug flow reactor, then it really, it shouldn't change too much. In reality, there's going to be some friction along the edges, there's going to be some diffusion happening and things like that. So it's not truly a perfect, again, ideal reactors are not ever totally realistic. But you can imagine that it works pretty well, because if you've ever taken, let's say, a hose, a yard hose that's been sitting in the sun and it's really hot, and you wanted to, let's say, wash your feet or something, you turn it on and there was water sitting in it, it will take a little while before the cooler water that was not just sitting in the sun to reach the outside. Now that means that it's flowing like a plug, right? So at some point there was water in the pipes underground or inside that's cooler, and that's making its way through, but it hasn't reached you yet, and it hasn't been mixing with the hot water. So the hot water stays as hot as it has been, is coming out until the plug of the cold water comes out, and suddenly you have a change, and now you're getting the cooler water. So that's what we imagine as a plug flow reactor. So if we have some reaction happening that entire time, that's a long time the water has had time to undergo this whatever reaction we're putting there, or we're designing, and so it's sort of a longer time frame to use. So sometimes it makes more sense to use a plug flow reactor, especially if we're trying to get a very a very low treatment level, so there's very little stuff remaining. Okay, so let's talk a little bit more about how to actually put in a mass balance here. So a batch reactor, no inputs, no outputs. We assume perfect mixing. And typically, if we have one reaction going, our accumulation rate is just simply going to be equal to the reaction rate. So dc dt in this volume would be equal to the rate of change in that volume. Now, there is a case where we can reach a steady state. So steady state meaning the accumulation goes to zero. Just as a reminder, we say steady state is when our accumulation term goes to zero. And if you think about, like, you have a reaction going, well, there's no way that the accumulation can be zero because there's something reacting. That means it's either growing or it's being destroyed. And so if you're tracking C in this chamber, then if you have something producing C, then of course you have accumulation of C. If you have something destroying C, well, of course it's a negative term of accumulation of C. The only exception there would be you can have multiple reactions. So bacteria, for example, might be growing and dying at the same time. That's actually quite typical of bacteria. So if we have we could have a scenario where we had accumulation equals some growth reaction minus some decay reaction. These guys both go to zero in a batch system because we have no water crossing our boundaries. And so in the one case where we have a growth and a decay reaction, we can get at steady state, then the growth reaction equals the decay reaction. And I'll say if we have only one reaction, or really only one reaction direction, you could have multiple decay reactions, I guess. Then we never arrive at steady state. Okay? Is that making sense? Okay, so then how do we put it actually into a term then? We wrote it up here, V dc dt equals RC times V. So typically what we'll end up doing is canceling out the V's and say dc dt equals that R of C. And we, if you remember, we defined that based on what reaction order that is. So we'll come back to this in a minute to look at an example of how we would put that into practice. Okay, the CSTRs then, we have continuous input, continuous output, perfect mixing, and so we would describe this with a Q going in, Q going out. For the sake of our class, we're not going to consider any cases where Q is going to be different, you know, a reactor that leaks or rains so that the Q going out is more than the Q coming in. We're not going to bother with that type of situation, and those are pretty uncommon anyway. So we'll have Q be constant across. We'll have some C, concentration C naught coming in, and some concentration C leaving. I already mentioned the fact that if we're completely mixed to perfectly mixed, whatever C happens to be inside of here is the same C that's leaving. We're going to have some volume, and then of course some, you know, it's mixed, and some reaction term. So in this case, we would say in the volume, our accumulation, the change of C over the change of time, is going to be equal to the inputs. We could have multiple. In this particular scenario, we just have the one, Q times C naught, minus the outputs, Q times C. And when I say output, I mean flowing out, right? This is a advection. This is a transport of the stuff away, out, the effluent, you could say. And then some reaction term in the volume. So you'll notice last time I was able to cancel the volumes for the batch system very straightforwardly. Like this is our mass balance here, by the way. Our mass balance equation started here, and we had essentially plus 0 minus 0 for the inputs and outputs. Here this was a V that we crossed through and said that was, we're getting rid of that. So in our current derivation, we have the V there, but it doesn't make sense to just cancel it directly right here. I mean, I guess we could divide everything by V, but we'd also have to divide these by V and all that. Okay, so here's the startup for our mass balance, right? This is where you start. This is writing out the accumulation term set equal to these other terms. Now, if we have a steady state, which is pretty common with CSTRs, we actually like that to happen because that means we have good control over what our system is doing. So if, and I'm abbreviating, it's not my, I mean it is my initials, but I'm not referencing myself here. I'm talking about steady state. So if at steady state, then this becomes zero accumulation of stuff in the box. We might have stuff being removed, but the amount of stuff in there is constant over time. So C has become, like we've achieved a continuous drop from C naught to C, and C is now at a level spot. If we change something about the reaction or the reactor or the flow or something, then we're probably in a situation where we do not have a steady state, and we have to then do some integration with this part. But typically we like to operate in a situation where it's a steady, a constant, no accumulation of C one way or the other in here. Now C might be changing in terms of, like, we want C naught to be different than C, but the C that we've reached is not changing, all else held constant. Okay, so then we have 0 equals Q C naught minus QC plus some reaction term. Okay, so that's the startup for these reactors. And what I've done so far is just kept these reaction terms generic to show you how we're putting these reaction terms into the mass balances given the different reactors. So I think we probably have plug flow reactors here, yeah. So we'll talk about this one, and then we'll put the two together and say, okay, well, how about this particular reaction order in this particular reactor. Okay, so first, plug flow reactors. Again, we can look at this as accumulation is input minus output plus reaction. But the reactor itself has some interesting assumptions. We see that we have continuous input, we have flow coming in, and flow going out of the reactor. But our mixing condition, as I mentioned earlier, is confined to just inside these infinitely small little hypothetical plugs. So those are mixed within themselves, but they're not mixing with their neighbors. So that means that essentially we have a little tiny batch reactor that's flowing along, kind of like it's on a conveyor belt. Now, technically, there's another way to look at it. That would be like a moving frame, where these things are moving, and now it's over here. There's another way to look at it, where we have multiple of these small little plug-style vessels. Each of them are well mixed inside them and flowing from one to the next, and so on. And so that would actually be an infinitely large series of CSDRs, right? Because each of these are well mixed. You have an input and an output and a reaction happening. That means if we imagine each of these little plugs as a tiny volume that is well mixed, and you can freeze them in place, you go into out, and all that. That's another way to look at it. I suggest you kind of don't think too hard about that, because the simplest way to look at this is to take it as if it's a batch reactor on a conveyor belt, because that means you can take the simpler version, the batch, and take the math that we will look at for understanding the reaction in a batch system, and the only change you need to make then is to account for how much time the water spends in our reactor. And you'll notice this drawing here has the tau, so time equals to tau. So we've talked a little bit about theta. Some people write it as tau, and this is our hydraulic retention time. We have a slide on this in a moment. So when we take a look at our math for a batch reactor that has a reaction that occurs over some time, when we want to analyze a plug flow reactor, we do the same thing as the batch, but we design it with we put in the time value as the retention time. So how much time did the water actually spend inside the pipe as our key amount of time. So in the difference there being, you could do a batch, a 1 liter batch system here, right? Give it 10 minutes and then pour it out, then fill it up again, do another 10 minutes for the next liter. Or you could have a pipe that travels, I don't know, maybe 20 meters or something, some flow rate going through it such that it takes 10 minutes before water flows out, and then what you have is a plug flow system that's continuously flowing, but you're getting essentially batch reactions and you're getting continuous output. Whereas with my 1 liter, I had to sit here for 10 minutes, empty it, fill it, start the reaction again, set a timer, go 10 minutes. Whereas the pipe example gives you that full 10 minutes of treatment just like you planned, but you never have to stop it, to interrupt it or anything like that, and you can scale it up accordingly. You just have to design the system so that it spends 10 minutes in there. So that's the difference there, and it becomes quite a convenient and straightforward analysis if you do it that way. Okay, so hydraulic retention time. I just mentioned this, and a reminder, I expect you to know this. Theta is V over Q, right? This is, for example, cubic meters. A flow rate might be in cubic meters per day or per second. I guess I have seconds here as an example. So theta is in seconds. Okay, so that's our hydraulic retention time. That's the amount of time the water spends in the reactor. And I have a little video here I've pulled up, and we can take a look and see kind of an example of a plug flow reactor. And this one has a tracer test so we can see the water flowing through it. So you can see here this the tracer die is kind of being added continuously, and we just got water flowing slowly through. You know, thankful for the die because you wouldn't see the water flowing at all if not. And if you ever go into it, or if you're ever interested, these tracer tests are a good way to describe how ideal or how non-ideal a reactor is. We're not really going to dive into that, but just while it's playing for a moment, you can see some areas of the water are really, or of the reactor, are really not mixing very well. So we see darker clumps, we got more dye, less dye in certain areas, and you'll see like this pocket right here will ultimately be kind of a dead zone is what we'd call it, where it's not really getting any mixing with the water, that it's almost as if that's just a wall because the water is kind of avoiding it. So whatever pocket of water there is not even getting, it's not, that volume of the reactor itself is not useful. And so what you would do in a tracer test like this is you'd have some point at which you'd measure the amount of dye coming across. So if you watch right here, right now we start having some dye come across, but it's a small amount, and it's growing now, and the longer we go, the more dye comes across there. So that's what a tracer test is like. That's also showing plug flow in a not quite ideal system, but that kind of should help you understand what I'm talking about when I say like there's this plug of water, it's coming, and eventually it will go out. All right, so with that, we've got about 20 minutes left, and I want to walk you through combining the reaction order into a reactor to give us some mass balance equation that we can solve let's say for the amount of concentration in a system. Now, sometimes we're not going to solve for concentration. Maybe sometimes we have to find the starting concentration. You'll see that we are able to do that. Maybe it's solving for the volume required for a particular setup. You'll see we should be able to do that too. So it doesn't, when we talk about setting up a mass balance or solving a mass balance, we're not actually talking about any one particular thing, so it can get a little confusing. What we're talking about is setting up a mass balance that describes the balance that that exists because matter cannot be created or destroyed. Based on that principle and how we can draw and confine the system so that we can set up a mass balance to describe it mathematically and then solve for whatever we need to. Okay, so that's why the term mass balance, when I use it or when you hear other people use it, might feel quite general. Find the mass balance, derive the mass balance, or whatever. But it's aimed at giving you the platform to find something. So let's start with a couple examples: batch case and a zero order decay. All right, so, and the goal here I have written is to use the reaction order that we learned about to insert the correct reaction term into the mass balance and then solve that mass balance. So, for a zero order decay, and by the way, before I launch into this, I'm just going to show you the decay today. Those are the more common ones that we do, but you should be able to do these on your own for a lot of the class. So it would be well worth your time to, on your own, do first order, zero order growth reactions, just to prove to yourself that you can do it and see what that looks like, how that would change these equations. For these, the batch cases and the CSTRs that we'll do. I'm also going to say that what we're dealing with right here are the simpler or the more common cases, but the skill here is what I care about you learning. It might be a little bit helpful to commit the results of these derivations to memory, but I do want you to have the skill of deriving this. It will help you in the course, and this really is how we need to approach these systems in order to do so with the flexibility to handle new stuff or situations that are a little bit different, right? So these are foundational skills, which is why I'm giving a full lecture on it. And you maybe could get by and get a C in the class if you just commit the end results here to memory and just hope you get it right on an exam or whatever and all that. Some people do try to do that, but I do suggest you get familiar with this process here. Okay, so a batch case, always good to draw it up. We've got something stirring, some beaker of water or whatever, maybe a tank, swimming pool. It's got water in it, it's stirring. So the reaction inside, we've got some volume and some reaction. The reaction inside can be described as dc dt equals negative k times c to the 0 power, because this is negative for the decay, 0 for the zero order. So we can write this, if we put this as a mass balance, we will say in the volume we have dc dt happening, and that's going to be equal to negative k times c to the 0 is 1 in that volume. So the accumulation in the volume is equal to the reaction in the volume. And by the way, when I write the accumulation term, this is always a v times dc dt. So when I wrote it right here, that might get a little confusing. So let me just elaborate a little bit real quick. So accumulation is going to be equal to what's coming in minus out plus V times R of C. I'm going to write it this way so we see this goes to 0. This goes to 0. What we're left with is this is in that volume, what's accumulating is dc dt. It looks, it is a lot like that, but that's not what I'm trying to keep these two a little separated. And so this V times R of C is now the only thing left. And so we would say V times this, times negative K times C to the 0 power. Okay, so this goes in to here. So now we have V dc dt equals negative kV. I'm going to go ahead and divide both of the V's, and we'll have dc dt equals negative kV. All right, so now we are, oops, added that V back. So negative K. So now it's very straightforward. It's quite simple, but we do need to integrate to get rid of all this. So what we're going to do is split this and say we'll take the integral of dc equal to negative K dt and integrate the dt from, we'll go from time 0 to time t, and over here we'll start with some starting concentration, C naught, to a final concentration, C. So when we integrate on the left, this just simply becomes C minus C naught, what we started with, and on the right, this would become negative K times T minus K times 0. So minus 0, I'm just going to leave that off. So that's our integration, right? So that becomes, we can solve for T, we can solve for K, we can solve for any of this, but I'm just going to go ahead and put it in the form of solving for C. And so we'll say C equals C naught minus KT. Now what's interesting here is this is stupidly obvious. If you stop and think a moment about it, if I told you you are taking, let's say, $20 out of your bank account every week, you start with $100, it's been 3 weeks, how much money is left? You'd say to yourself, well, obviously 3 weeks times 20 is 60, so you have 40 left, right? You do that in your mind without even thinking about it, right? It's like such a no-brainer. But the other way you could do that is say, okay, well, how much is left? Okay, is going to be equal to what you started with here minus the amount it's changing every time period, the $20 per week, times how much time went by, which was 3 weeks, right? So you could get that answer by doing a full mass balance on a 0-order decay in a batch reaction. So it becomes a little painful to think about, why did I need calculus for that? But it's also kind of neat that, hey, we just did all of that calculus, all of this process got us to the same thing that we can see. Now, if you had multiple reactions here, it might not be as obvious, or we could consider things that could complicate it as beyond what our intuition could do. 0-order, though, is typically pretty straightforward. Okay, so now a first order, we can take this scenario. Again, if we started with our accumulation equals in minus out plus V R C. In fact, I'll go ahead and just write this as V dc dt is equal to that. These are going to 0. because it's a batch system, then we're set up in the same way, right? We have V dc dt equals negative V k, and this time we have c to the 1 power. So get rid of the v's, we're left with dc dt equals negative kc. And now when we need to integrate, we have to do something a little bit more, and here's where the little bit of calculus that you need to recall and the one algebra trick combining with that, and we'll get a nice solution that you've seen a million times and you'll feel good about, I think. And that is, first of all, we're going to separate the like terms, so we'll have dc on the left divided by c, and over here we'll have negative k, do the same thing with dt, integrate that 0 to t, and over here on the left, I might have said left, I meant right a moment ago, this c naught to c. If I was in person with you, I'd ask you to tell me what the integration of dc divided by c is. And I'd let you think about that a moment because you might recall it from calculus. So feel free to pause if you want a moment longer. And by the way, that's one of the nice things about live streams, you could pause them. But if you don't remember, here's the answer. So the integral of, we'll write it as 1 over x dx. That might be a little more familiar. And the answer to that is the natural log of x. So in the case down here, the integration of dc over c is the same thing as here. So this becomes the natural log of c minus the natural log of c naught. So we had to go from c naught to c equals negative kt. So from this, like that's the derivation, the integration, excuse me. Now from here, what we'll see is we just can use one trick from algebra, and that is that if we have two log terms like this, adding or subtracting, we can actually combine those in a convenient manner. So this becomes the natural log of c over c naught. So there's your one calculus feature, and here's your one algebra feature that maybe you didn't remember, but now you do, and I suggest you try to remember that because you may need to do this. So ln of c minus ln of c naught becomes ln of c over c naught. And that is still equal to minus kt. And then, okay, one more algebra thing here. If we want to get rid of the natural log, we raise e to the power of both sides. So this becomes c over c naught equals e to the minus kt. I expect you probably remembered that one. Okay, so if we solve this for c, this becomes c equals c naught times e to the negative kt. Now, I know you've seen that before, and you probably also saw this way back in algebra. If your school was anything like mine, or your class, I learned the PERT equation, right? P equals e to the RT for interest rate equations. Or maybe, if you had some starting balance, you'd have P naught. But at the end of the day, what we're saying here is that in the growth equation, we have a positive here, but it's that k times time. So it's actually that interest rate equation is a first order equation applied as if it's in a batch system. Got some batch of money, right? And something's operating over the course of time. So you've seen this before. Should look very, very familiar. This is a first order decay reaction for C equals C naught times e to the minus kt. Okay, so now that we know the batch, we also basically know the plug flow reactor, but instead of putting a time here, we could put a theta. So we'll say instead of t, if we put in theta right there, then we've got a situation where we're solving for our for a plug flow reactor. It's really as easy as that, and we remember that this is V over Q. So by doing it that way, we are essentially able to perform our math in a way that gets us access to the reactor dimensions, the volume, and the flow rate, I guess the process conditions, and just put that in there. Otherwise, the math is pretty much the same. Okay, so please do ask questions if you've got any. I'm going to move on to the last portion, but if you do have questions, happy to answer them. You just add in a comment. Okay, so then last, our CSTR case, and then next time we'll start with some practice here. Okay, so for CSTR, what we're talking about, again, to draw it up, we have a continuously stirred system with a flow rate coming in and a flow rate going out. Some amount of concentration of C leaving, and some initial C coming in. We have some volume, and we have some C. We also have some reaction happening inside. So there's our drawing. So a zero order decay reaction put into this context. Our accumulation is going to be happening in V dc dt. That will become equal to, and by the way, most of the time, I mentioned this, but most of the time with CSTRs, we like it if we can operate in steady state. So I will also make a steady state assumption for these derivations. So if you ever had a situation where it was not steady state, again, there's a reason why you'd want to be able to derive these on your own. But for these ones, we'll assume steady state. So we'll get back to that here in a second. So then we have, so our accumulation is going to be equal to what's coming in, that's QC naught, minus what's going out, QC, plus that reaction term, which happens to be a negative K times C to the 0 power in that volume. So the accumulation term we're going to assume is 0 because of steady state. Then we're left with QC naught minus QC minus KV. So if we want to solve this for C, all we do is add the QC to the left side, to both sides, and we're left with QC naught minus KV. And now we can divide everything by Q and say this is going to be C equals C naught minus K times V over Q, which might remind you is theta, right? V divided by Q equals theta. We don't have to leave it that way. We could leave it as V over Q, but sometimes you'll have a problem where maybe you're given theta and you need to solve for V. Maybe you're just given, just be aware that these the simplification can help, but you can also expand it back out if you need to. So this would be a typical derivation for a simple CSTR, zero order decay at steady state. So if listen to how many qualifiers I just gave it, right? So this is simple, meaning only one input, one output. This is zeroth order decay reaction happening. And this is at steady state. So if you want to memorize formulas where I think you should derive them, you probably ought to, if you want to do it right, also memorize all the conditions that got you there for the derivation. So, yeah, just keep that in mind. So another example here, first order decay. This one in particular will be used, we'll see it quite often. So of any of them, if you want to memorize something to double check yourself, yeah, this one might make sense. Okay, so let's do the same thing. We have zero accumulation. I'm going to go ahead and just make that statement here, like I did there. What's coming in is QC naught minus what's going out, QC, plus our reaction term, which is a negative K times C to the 1 power times V. Now, right here we have two C's, terms that we need to combine, and we have two Q's and a V here. I'm just going to go ahead and divide everything by Q. You don't have to do it yet, but I just like to go ahead and do it at this step. So 0 equals C naught minus C minus K C theta. Again, the V over Q there is pretty convenient. So then I just need to get the C's by themselves. So I get C plus K C theta equals C naught. And then we can extract the C's here. So C times 1 plus K theta equals C naught. And if we solve for C, we get C equals C naught divided by 1 plus theta K, or K theta. Now, I mentioned not all the time you're going to want to solve for C exactly. Sometimes you'll want to solve it for C divided by C naught. What portion remains, right? So in this case, that's a nice easy one to find. What portion remains? That's 1 over 1 plus theta K. So your equation becomes quite simple. You'll see these forms of it quite often. Okay, so that's all we have time for today. Like I said, I'm going to try to speed up the next few sessions and decide on what exactly the ground I need to cover. But we'll get a little bit of practice in on this next time to start off the lecture. And I do plan to be in person. I truly doubt I'll be contagious or anything by then, and I probably could have showed up today, but definitely still think I'm contagious. So I appreciate you all, the patience. Again, I'm so sorry about Tuesday and the message not going through. So have a great weekend, and we'll see you Tuesday.